Hello, and welcome to Advanced Statistics, Statistical Techniques. Today, this is what we call bonus, right? This is off of the chart, so to speak. If you ask me, is that going to be on the test? No, it's not going to be on the test. Granted, there are no tests, so that's pretty easy to say. So the first module we talked about Monte Carlo, right? The second module talks about Markov chains. So turns out there's this thing called a Markov chain Monte Carlo. And so I thought we would spend some time going over that. Uh, it is potentially fairly complex, certainly beyond the scope of what is in the outline. Feel free to skip this if you're so inclined, although it could be useful and it could be interesting. So with that, I'll go ahead and get started. Also, I wanted to tell you about something that may be old hat to you, but it's new to me. Thanks for joining, John. So I was just saying, the material I'm going to talk about today is the combination of Markov chains and Monte Carlo, called Markov chain Monte Carlo. MCMC is the abbreviation. If you asked if it's on the test, no, it's not, because it's there are no tests, right? But it's also beyond the scope of really the deliverables in this course. That being said, it is kind of interesting, so I thought I would go through it. I alluded to it last time, so we'll see how it goes. Before I get started, any questions, anything you'd like me to discuss?
No, this sounds like a really good topic. I got to thinking about how, the Monte Carlo sampling method could produce better initial state probabilities. So
Yep.
be good to hear you talk through that and
Cool.
kind of get it going. Yep.
Yep, sounds good. So before I get going, one of the things that it may be old hat to you, but something I found because I like having it. Whenever you run in something like Databricks in the cloud, it lets you know how long every sort of thing you do takes, right? Uh, Jupyter doesn't do that by default, but you can install an extension called AutoTime, right? So basically you do the installation. If it's not installed, it'll install it for you. And again, IPython-AutoTime. And then you basically do a load extension, AutoTime. And after you do that, every time you run a cell, it tells you how long it took, right? So that's kind of handy, especially if you're getting into any sort of optimization. So kind of cool. It's one of those things you may be familiar with, but if not, pretty cool.
Yeah, it
So,
is. I'll,
yeah,
I'll add that. I did also get my R running in the Jupyter environment. That's been pretty cool too.
yeah,
I love Jupyter.
very
Yeah.
cool. Yeah, big fan. You get to the place where you wonder how you wrote any code before it, right? The things that I'm going to show, I did not create. I borrowed from various places. I'm giving them the credit for it here. Machine learning mastery.com/Markov chain Monte Carlo for probability. There's a mouthful. Probably could have came up with a shorter URL if they had tried. But anyways, the motivation for doing MCMC is it's about dimensionality. So uh, generally speaking, whenever you're trying to approximate a distribution, a lot of times you'll use a grid method to do so. You'll basically enumerate over some interval the various features inside of your space and determine kind of what it looks like in that way. And we'll talk about that in a little bit, or I can actually jump over to it. So another resource, I stumbled upon the Bayes Rules book, but basically it talks about the concept of doing grid approximation, right? And that's the primary reason is basically whenever you get by, and the spoiler here, when you get above about 3 dimensions, meaning basically three features or three variables, it starts getting to be a problem because you've got a lot of different combinations to consider. Two, pretty straightforward, X and Y, that's not too hard. Even three, you can go into Z, but at the point you get past that, it kind of starts falling over. So, and the basic idea here, as you can see, is that the finer your granularity in your grid search, the more robust your result is going to be, but you're trading off computational time to do that. Um, and this is where the basic idea of as you reach a higher degree of dimensionality, being able to do the certainly exact inferences intractable. It becomes computationally limited to where you pretty much can't do it. And especially whenever you're talking about figuring out, trying to basically do inference. So you're trying to figure out what is causing what, right? And so instead, we basically will shift over and start using Monte Carlo chains, right? And that's where you combine together that cool thing about doing some sampling in repetition and determining kind of aggregations and so on. Combine that with then for each one of them essentially doing some Monte Carlo, some Markov chain calculations. So it ends up being pretty cool and working pretty well. But Monte Carlo into itself can't do it. Markov chains into itself can't do it, but combine them together and you get something pretty cool. So as a review, we'll review in a moment, but basically it's about sampling in high dimensions, and that's where MCM comes in. And pretty much it's kind of, from what I can tell, the way to do high dimensional distributions. If you're trying to determine something that has got a fair amount of features, it's one of the better ways to do it. It's been around obviously for quite a while. A lot of it, along with a lot of the other kind of things, came out of our desire to create, weapons of mass destruction, right? So, kind of a unfortunate sort of thing, but yet that's how progress often gets made. So, review Monte Carlo, random sampling, and basically coming up with an approximation of some desired quantity. Pretty much. Pretty simple, really. A loop, some sampling, some aggregation, and some analysis of the things at the end, right? That's pretty much it, right? So the idea is that you can efficiently draw samples from the target distribution. So that's where it comes in. Markov chain, it's basically the idea that your next state essentially is based on your current state, right? That's kind of it in a nutshell. And with a obviously stochastic sort of process, so that there's randomness involved as well. And it's about kind of limiting the behaviors of the sequence is what it kind of comes down to. So you're figuring out the likelihood of various things going various directions, rolling the dice over and over again, so to speak. So it's actually a pretty good example of the snakes and ladders, or chutes and ladders, the old game we played as children, to where you roll the dice, so you've got some randomness there, and it's going to change your position on the board. So that's essentially your state representation. So you can think of it as it says, a random walk in one dimension. This is a simplistic Markov chain, not so much the things we're doing, which are about the Markovs. It's still Markov, but it's not just a single chain, but a set of chains, essentially. So you're doing the matrices versus just one particular state to another. So the combination is pretty much you need your data, and then you combine the things together, and we'll get into a better example. And that's what I prefer to do in general, is look at code. Going into the algorithms, there's lots of different algorithms that have something to do with Markov chains. The ones that we hear the most about are the Metropolis-Hastings algorithm and Gibbs sampling. Those are kind of the kind of first two. The Metropolis-Hastings algorithm is supposedly one of the easier ones to understand, but I'm not going to go into a lot of the math, because while it's relatively easy to understand, that's not the point of getting into that much theory here. But you can go out. I might try to share this notebook, because it's actually fairly cool. Spent a fair amount of time. Also, another one. You notice the spell check. That's another thing that I figured out, because the person that I'm enhancing their notebook couldn't spell at all. So I figured out how to go in and turn on. It doesn't correct your spelling, but it will tell you what is incorrect. So I'm trying to find the right screen. So inside of you can basically go to MB extensions, uncheck this and make sure that spell checker is checked. You may have to install it as well. It's another extension. But after you do so, if something is misspelt, see, so here's a good example, right? So in sure, pretty interesting, really, that it's that bad. Anyway, so another cool tool, spell checking, and you can see the little thing here, right, that shows you that. So again, my journey today was about extensions, but anyway, moving in back into kind of how they work. The algorithm's about coming up with a way of sampling in these next state probability distributions, using something similar to Gibbs, right? And Gibbs I actually talked down about next, down here. This is the Gibbs sampling, but for now we'll go through this one.
Are you sharing your screen right now?
No, I thought I was, but no, I'm not. So we'll go back up.
Gotcha. Okay.
There we go. Sorry about that. Yeah, that's a rookie thing. It was odd because my video wasn't turned on, and it usually defaults to being on, so I don't quite know what happened there. Sorry about that.
No worries.
So fortunately, it'll be in the recording. Not that that'll help much. So again, here's the auto time install I mentioned, and sorry about that. That kind of really diminishes the whole experience, right? So basically, rather than doing a PowerPoint this time, I'm working through a notebook, and I took the notebook by basically pulling together from 2 or 3 different places, trying to clean up their stuff. And one of the things that I did install and turned on was so inside of let me find the right window again. Inside of Jupyter, if you go over to NB extensions, I had to, I think, turn this off, which is disable configurations without explicit compatibility, and make sure that spell checker is turned on. If you do that, then whenever you're going into your markdown, if it's misspelt, or it doesn't know what it is, it will turn it like this to the red, right? So it doesn't suggest, and it's weird because I've got Grammarly's plugin installed here, but it doesn't work in this environment for some reason. So anyway, the person I borrowed these notebooks from, horrible speller, or else just didn't go back and take a look. I've been trying to get them, but it's there's a lot to get. So anyway, back to not going into too much of the math involved. So the Metropolis Hastings algorithm, about whenever you're dealing with things that, and it's kind of a theme, same thing it was with Monte Carlo, right? You use this sort of approach whenever your dimensionality is so high that probably it's excluding other stuff. So you've got too many features, and it is kind of the one tool that will work for this particular set of problems. It is going to be an approximation. There are some downsides to these sort of algorithms, right? So it may get stuck oscillating, for example. It may not converge, which is one of the things with any kind of essentially a simulation. You want it to converge to a solution, and it may not. So those are challenges. To help with that, you'll do things like adjust essentially the increment or the granularity. I showed earlier, whenever I was sharing my video, whenever we talk about grid approximations, it's about the granularity of the iteration. So it's how big is essentially your delta, your increment. Similar sort of concept applies whenever you're dealing with these sort of approaches as well. The difference being you're not doing exhaustive sort of grid sort of search or applying essentially a function to every incrementally value in a set of dimensions. Instead, you're basically going through and randomly picking, because of the Monte Carlo sort of approach, something, and then you're essentially applying the Markov chain to that, right? That's kind of the basic idea. So combining together a separate sort of resource, I found some examples of doing the Metropolis Hastings in a code sort of approach. They go through the various sort of descriptions of what it is exactly, from the mathematical stuff and proving out kind of how it all works, which is interesting. But I'm more about application, right? So how can we use this? And it's actually fairly cool. There were a few. It's like every example you find, right? They may or may not work, right? So finally got it to work after quite a bit of work. I'll go ahead and start stepping through it. And so the basic algorithm here, target is part of it, and a lot of times these things are about basically figuring out if it's a hit or a miss. That's kind of what it kind of comes down to. So it's reminiscent of the approximation of pi algorithm we talked about with Monte Carlo, right? Similar sort of approach, and you figure out basically similar sort of patterns of it's in or it's out, but more so in a sense of trying to approximate your value. So it takes a bit to run, and that's part of why I went ahead and installed that handy auto time feature. And while it's doing this, it's essentially iterating through 20,000 times. So that's what we're doing here. Calculating the various values, determining essentially how well it did it. When it's all said and done, we'll be able to plot what it did against the actual distribution and see how well it approximated it. And there we go. Took not real long, 35 seconds. And then here we can basically do the plotting of what it figured out versus, so the true posterior versus the distribution of the prior samples. And you can see got pretty close, not too bad. And you're looking for pretty much a uniform distribution of those samples. Part of what's going to make that happen is we are doing a uniform here. But anyway, it is pretty interesting. And it does let you essentially come up with a way of figuring out if things are actually converging. So that's at a very brief level that algorithm. Moving over back to the Gibbs sampling, it's a similar way of constructing Markov chains, basically with conditional probability given the state you're in from the prior sample, right? So you do some construction from sampling, and you essentially are changing one random variable at a time, and so on. So this is without going into a ton of the examples, we'll go ahead and get down into the code because the code is the more interesting part. So we start off defining a set of functions, and the names, especially make plots, pretty straightforward, and it did need a little bit of a fix up here. There's been a change in the library since when this was authored. Some functions, so the likelihood of Bernoulli with n trials and z successes and so on, and then theta being calculated as well with lots of math. So anyway, going ahead and making the theta and then creating a grid and then kind of pretty much doing an analytical solution. Again, similar sort of results, and producing the distribution sort of things, and also in the three-dimensional space. This isn't as pretty as the original one because apparently whatever it was that got deprecated was made it look a lot nicer. Let's hop over and see if we can see the original one. I skipped over this bit about using the traces as a way of determining convergence. This is showing essentially coin flips and seeing that they do indeed converge. But whatever reason, the nice little edges on the thing went away, or else I don't quite know how to make them. But anyway, back to the topic. So we can go through the the sampler. Pretty much we've done all this. And an additional ones as well. There's something I was trying to think, but I'm forgetting what it was. But a very high level, this is kind of what it is. So again, there's the concepts of iteration, doing essentially some form of sampling, some sort of calculations upon that sampling, and then combining it together so that you can keep it over time. So that's basically the basic idea of these. It is the combination of the two things that we've been talking about, both the Markov chains and Monte Carlo. What I was really wanting to talk about today was PageRank, because it is an interesting application of Markov chain, but it wasn't coming together quite as well, so I'm not as prepared as I would have liked to have been. But this is still, I think, quite interesting. It does get into being a pretty advanced topic pretty quickly, but it is something that, as a data scientist, you'll probably spend some time researching as the particular type of need surfaces, right? So the takeaway I'm hoping for is that hey, if I've got something that I need to approximate a distribution on a high degree of dimensionality so that I can do some form of essentially regression, then MCMC is the way to go, right? And if you remember at least Monte Carlo and Markov chain, Google those two things, you'll probably find this. And that's the key thing to take away, is that based upon the problem you're being presented with, what you do with it. Also, another thing that I'd hoped to talk about was using Markov chains to predict the location of ships based upon their segments. But again, a demo that didn't quite demo. What I wanted to do was tie in together Databricks and Spark, and the use of Databricks machine learning to do it at scale, because it enables you to do things similar to what you do with PageRank, right? Again, it's at scale. You're doing Markov chains to determine probabilities. So the PageRank algorithm is basically a Markov chain. The idea being, what is the probability that I, as a web surfer, will click on a given link and go to a certain page? And in particular, what are the important pages? And so it's a way of basically calculating the importance of a page, and also the likelihood of a person going to a page, all things being equal, right? So then if that's basically how Google became Google, was they created the algorithm, and the algorithm was initially called Google, and then that led to the creation of the company and the search name and so on. So both of those share the concept of both the Google search and the figuring out where boats are going based upon where they left from and the direction they happen to be heading over time, are based on the concepts of essentially Markov chains, right? Of figuring out the patterns over time and the likelihood of based upon where they are, because apparently whenever you're talking about ships and like shipping containers and cargo vessels and all that, it's not exactly like aircraft, where you have a pretty much a relatively prescriptive flight path that you have to follow. Rather, they have a lot of latitude in their navigation. And so whenever you're figuring out where they're going, it's non-trivial necessarily, because it could be challenging. Also, though, you do know they're likely to pick the path that is the most cost effective, in the sense that it's going to reduce either currents or distance or something, so that they're not likely to just head in some random direction, then change and go some other direction, right? So that's where, again, time series, and you have data that shows you, or you can use it to determine the probabilities of transitions over time. And you can do that with PageRanks. You know whenever people are going to certain pages, so you can gather that information. Plus you also know the links to and from various pages. And in both situations, though, you kind of have to handle the case that there may be data in there that is kind of incomplete. So you have to avoid kind of black holes, so to speak. Maybe it's going someplace that you don't know about, or coming from someplace you don't know about. In the case of things like PageRank, you may not have the entire corpus of all of the web pages in existence within your data set. So if that's the case, it could be targeting something you don't know about. So your algorithm has to handle that appropriately as well. So with that, I've talked for a while. I'll pause, see if you have any questions.
Well, so far so good. That makes a lot of sense.
So the intent here is to show, hey, this stuff really has application, right? It's not just a random topic. And it's actually, I mean, the guys at Google did quite well coming up with something based off of Markov chains. So maybe worth studying, right? And also other sort of algorithms. It's also in that scenario, you're thinking of pages as your nodes and your hyperlinks as your links, right? So it fits very nicely. And also the edges would have a probability of being clicked that either would be determined based upon the importance of the site you're going to, or it could be based upon previous captured information about users' traffic, of where they've went, what they've clicked on in the past, and so on, so that you can do an informed prediction of what it is they think you want to see in the future. And and it's really scary to some extent how smart Google has got of knowing, especially if you let them track you as an individual, of what it is that you likely are going to be looking for. So that probability distribution is getting pretty interesting, I'm sure. Because they also seem to be throwing in things like your location, right? So if you search for something, but you happen to also have received an email about an upcoming reservation at a hotel, say, then all of a sudden your search results starts changing a bit. So pretty convenient sometimes, but also sometimes pretty creepy, right? So anyway.
The shipping example is a really interesting one, because we have a tool at Cargill called, I think we call it Magellan, and it must be implementing some kind of a Markov model underneath, because it assigns probabilities to destinations based partly on where it left from. It predicts future legs of transit based on what's happened in the past. I really wonder if it's that, like whether it's if it's coming up on the West Coast, it's going to go to Long Beach, or I forget the port south of there, but it assigns probabilities, where 80% of the time a ship that's come this path from this port of origin has gone to Long Beach. So it's got to be something like that.
The notebooks I were trying to get to work, I think, is related to this blog post that I'm sharing. And basically it's definitely doing something similar to like what you're talking about. They go through the process. It's kind of interesting. They first thing they have you do is download a whole bunch of data from basically the locations of various vessels over time. So it's time series data. Then you download the various ports from a different page, which currently wasn't working. And so that's where it kind of went sideways, right? So I was hoping to show this one because it's pretty cool stuff. Then you go through and basically it essentially, I believe, I forget what they called it, segments basically the data into from here to here with a time, right? And then you end up constructing essentially a Markov model and then doing some prediction based upon where you're at, where you started from. It predicts the likelihood of where you're going. So it sounds like exactly what you're talking about.
Yep. Very cool.
And it's a compelling demo if it would actually work, but it's unfortunate because I was really kind of hoping to show that one too. But that's one of the challenges. If you were to sample pretty much any website, say Databricks or Microsoft's gotten better, but there was a time when they were really bad, and download their demos, it's probably about maybe 70% work.
Mm-hmm.
But part of that is things change, the libraries you're using change,
Yep.
and so on. But the that's a key takeaway too, is if you can solve the representation of it in a matrix form, a tremendous amount of work has been done to handle computation of matrix kind of data at scale. And that's where you move
Yep.
into the world of like Databricks and Spark in general.
Yep.
You can process 50 million records with no big deal, right?
Yeah.
Assuming you can afford to pay for the cluster. But yeah, that's pretty much it. How's it going with module 2?
Good. I submitted the assignment. The code was really pretty straightforward. I did a little bit of extra to contextualize it,
Yep.
but the the utility of all the different things you could use this sort of technique for, anywhere you can do matrix math, it's pretty amazing.
Yep. Yep. It's cool stuff. And it's especially when you're talking about kind of time series, and
Yep.
if you can figure out those probabilities, right? So if you can figure out the transition state probabilities, then you can do some really interesting stuff, and especially figure out how to change them, right? So if you've got a high bulk situation where people are in queues and they're getting out, then
Hmm.
figure out how to make that go down equates to money, right? So
Yeah. You got to reach them somehow. Yeah. It's cool how that opens up a business opportunity.
yeah.
You gain insight.
All right.
Very cool.
So we'll be moving on to Module 3 next week, and we'll see what happens then. So if you're watching, Eric, and you have any questions, let me know. Thanks for joining, John. I appreciate it. It's always better to talk to somebody than to an empty room.
Yep.
And if you have questions, let me know. That's what I'm here for.
Perfect. All right. Well, have a great night, and we'll see you later this week.
All right. Sounds good. Stay safe.
You too.
All right. Goodbye.
Bye-bye.